Hello, I'm Richard Zare. I'm a professor of chemistry at Stanford University, and I've had the great pleasure of giving Chemistry 1, Chemistry and the World About Us, a special course designed to satisfy the Distribution 7 requirement at Stanford University, a course for undergraduate non-science majors. This course has been for me great fun because I find it so challenging to try to tell people about the world of science and, of course, the most central science, the world of chemistry. When you go to various chemistry lectures, you carry away different things. Sometimes one of the most indelible experiences is a great lecture demonstration. But I must tell you that such things always represent a threat to the instructor, because it's quite possible for the demonstration to go wrong, or worst of all, nothing to happen. But when it works, the effect is wonderful, and you can remember for a long time what you're able to see with your own eyes at such a demonstration. Let me give you an example. Suppose we were to discuss the complicated coupling between a rotating and vibrating object. Sounds all very abstract and abstruse. What could one make of it? Yet an example will drive home how this can happen and how it can even be interesting. I brought along such an example. It's a toy called a rattleback. I have it in my pocket. Let me get it out and put it so you can see it. This is a piece of plastic, just clear plastic, of course in the appropriate Stanford color. As you look at this, you see that this object, with no magnets, no electric field, can simply rotate on this flat surface. Indeed, if I push it like so, it goes around, and because of friction, it slows down, and after a while, it comes to rest again. Now look what happens if we rotate this in the opposite direction. It actually reverses itself. And if you ask, how does this happen? It's quite complicated. Some of you have seen that if you take a hard-boiled egg and rotate it, it tries to stand on its tip. The same thing happens here. This object tries to raise itself as you rotate it and causes it to rock back and forth. Because of the way the bottom is cut, this rocking motion actually then is coupled into rotation, as you can see when I push down on this end, and you can see how this turns into rotation. Indeed, I ask you now to try to listen very closely as to what happens, because as it goes around, it then rattles and then turns back, which is why it has the name rattleback. Quite an amusing object. That's just one example. We had the great pleasure, the we in this case being Professor Alex Pines at the University of California at Berkeley and I, to invite Colonel Brian Shaw to deliver his world-famous lecture on explosives. He gave one such lecture at Berkeley and one at Stanford. With the help of many people, I was able to get permission to use, and I was able to pack Memorial Auditorium in the spring of '88. The lecture, I thought, was quite grand, and I want to bring you an example of such a successful lecture demonstration. I think you will see as you watch this that Colonel Shaw really gives evidence that chemistry can be fun.
But now I must point out that some of my experiments can be dangerous unless they are performed properly. This does not mean that they should not be performed. A motor car can be extremely dangerous if it's not properly handled. And during the past 60 years, some millions of people have been killed on the roads. During that 60 years, I have delivered this lecture more than 1,000 times, and I've killed nobody in the process. Statistically, therefore, you are safer in this lecture than you are on the roads of this country. However, In case there should be some smart guy who wants to make something out of it and claim damages, I issue a disclaimer. You are here entirely upon your own responsibility. Neither I, Dr. Palmer, Professor Pines, or the university accept any responsibility whatever for your safety, and unless you are prepared to remain here on those terms, now is your opportunity to leave. Thank you for your confidence. This evening, however, I propose to restrict my experiments to the conventional explosives. Because although they are less powerful, they have one great advantage as far as we're concerned. We can demonstrate them in a room of this sort more than once. These we can classify in two main ways, as mechanical or chemical. It is very easy to demonstrate a mechanical explosion. The only apparatus you need is a paper bag. You just blow it up, screw up the neck, strike it a sharp blow with the hand, and you get a mechanical explosion when the walls of the bag give way and the compressed air within is released. I'm trying to demonstrate it in a rather different way. I have here a small glass tube in which I've sealed up some water. I've colored it red, so that one might say it is more readily visible. And I'm putting it over a flame. Now, I always like to perform my experiments in duplicate or triplicate in case one of them shouldn't work. And so I have a second one here, and Dr. Palmer is fitting up a third one over there. Now, if you put a vessel containing water over a flame, you expect the water to boil when its vapor pressure becomes equal to that of the atmosphere. That, after all, is what we mean by the boiling point. But here you see the atmosphere in the tube is sealed up together with the water. So the pressure continues to develop. It is rather surprising how much pressure these tubes will stand. They're only thin glass ignition tubes, but if they're good ones, and they're not always, they will take a pressure of something like 40 atmospheres, say 600 pounds per square inch, before the walls of the tube can stand it no longer. And at that pressure, of course, the water is far above its ordinary boiling point. And so when finally the walls of the tube can resist the pressure no longer, and they give way, the water is converted into steam instantaneously. And so the steam is generated. The steam is generated at supersonic speed, and that is why you get that effect. Now you might think this is just a toy, but the theory of it is used in a commercial explosive. The mining explosive cardox consists of steel tubes containing liquid carbon dioxide, or at any rate carbon dioxide under pressure. And they have at one end a heating tube which can raise the temperature by means of an electric current. This, of course, vastly increases the pressure, and the bursting cap of thinner metal at one end of the tube gives way, and the carbon dioxide comes out of the holes at the end with explosive force and acts as a very good explosive on, for example, a seam of coal. No shattering effect, and of course carbon dioxide is a fire extinguisher. Now you might think that when this happens, the whole thing would come shooting out of the borehole like a shell out of a gun. Well, they thought about that, or found it out, and so they provided a couple of little arms at the end, which are also pushed out by the carbon dioxide to anchor it in the coal or whatever else it's been used in. An economical explosive because the tubes could be recharged and used repeatedly, but not used now as much as it was formerly. And so mechanical explosives are used to some extent. Another type was hydrox, which used a chemical mixture to generate a pressure of hydrogen and carbon dioxide. And so there is a use for mechanical explosives, but the use is limited. And however, the greatest explosion of which we have any record in history was due to precisely the phenomenon that you witnessed in those tubes. In 1883, the volcano Krakatoa, at the end of the strait between Java and Sumatra, was in eruption. Part of the crater was blown away, the sea rushed in, and it's thought that a cubic mile of seawater was vaporized instantaneously. Now, you've heard the effect of the instantaneous vaporization of about 2 cubic centimeters. You can't visualize what that of a cubic mile would be. The mind, so to speak, boggles at the immensity of it. But it is calculated that the effect of the explosion was greater than the sum total of all the man-made explosives used throughout history, and you can include in these the atom and hydrogen bombs. The tidal wave produced was 30 feet high on the surrounding land. It was still a foot high 5,000 miles away on the coast of South Africa, and even perceptible in the English Channel. The level there rose a couple of inches or so, and it caused the boats to tug at their moorings. A cubic mile or more of earth was pulverized and put up into the upper atmosphere. Some of it stayed there as long as 10 years, and it gave rise to a series of magnificent sunsets. The mechanical explosive can be enormously powerful, and it is used to some extent, but normally we rely upon chemical means. The burning of something containing carbon dioxide.
Slide on punch.
I'm reminded that I've left out one slide. I told you that the tidal wave was perceptible even in the English Channel. Punch had a comment on this. Policemen on the south coast warning the paddlers, Krakatoa has exploded. But it was no joke for the people on the spot, because some 30,000 were drowned as a result of that mechanical explosion. But as I say, although we use mechanical explosions, we usually rely more upon chemical means to produce the effect. The burning of something containing carbon to give a pressure of carbon dioxide, of hydrogen to give a pressure of water vapor, and usually there's nitrogen or its oxides there as well. And so I suppose we ought to illustrate the process of combustion. And I will do this by a simple experiment, which I don't know whether they see it in America. Schoolboys and girls used to see it in elementary chemistry classes in England, but on recent years the authorities have become so nervous about it that they prohibit teachers from demonstrating this. This, I think, is a great mistake. They say that they should warn people about the dangers of mixing things together, but a practical demonstration is far more effective. However, even though they see this experiment, they do not see it perhaps quite on this scale. The main supporter of combustion, of course, is oxygen. And so I'm going to fill this flask with oxygen by the simple expedient of pouring some liquid oxygen into it. And of course, as that evaporates, it will expel the air. And we can tell when it has expelled the air by a simple test. Obviously, it has. Now we need something to burn. One material that burns very readily. That's an indication of when it's finished. You see that? When it stops rattling, I know that all the oxygen has evaporated. One material that burns very readily is phosphorus. And so I have here a fragment of phosphorus. And I'm going to mop off the water under which we preserve it and lower it into a basin that I have on a little pedestal in there. Now, the combustion of phosphorus can be started very readily. The warmth of one's finger is enough to do this, but I prefer to use an iron rod. And whilst I'm warming up the end of this rod, let me draw your attention to what we have. It is really, you see, a mixture of phosphorus and oxygen, but by no means a good mixture, just a lump of phosphorus in the middle of the globe of oxygen, and so we can't expect a very rapid action. But when I touch the phosphorus with the rod, will you please extinguish all the lights that you can, because I think we may provide a certain amount of illumination. And so here you see the process of combustion taking place, but observe no explosion. And I am fairly confident that there won't be one for two reasons. One, because here was no intimate mixture of phosphorus and oxygen, but just a lump of phosphorus in the middle of the globe of oxygen. And secondly, because the products of combustion, although produced initially in the vapor state, rapidly condensed to the white solid which you see being deposited on the walls of the flask, mainly phosphorus pentoxide. And so we see by this that if by means of the process of combustion with a mixture you wish to produce an explosion, the conditions to be observed are, first of all, that it must be an intimate mixture, and secondly, you want the products of combustion to be gaseous so that they can exert a pressure. Now, it would be very interesting to find out if we can produce an explosion by means of phosphorus and oxygen if we have an intimate mixture. And there are various well-known compounds which would serve as a medium for this. Because you see, you cannot make a mixture of potassium, of an oxidizing agent with phosphorus. The most common available one would be potassium chlorate. But if you tried to mix potassium chlorate with yellow phosphorus, I don't think you would finish it. The probability is that it would finish you. It has some people. And so I implore you not ever to mix anything rich in oxygen with anything combustible. And as you see, phosphorus is extremely combustible. It is done with red phosphorus. The composition of toy pistol caps contains red phosphorus and potassium chlorate, but the makers never mix more than a few ounces at a time, and always wet. And this is a point I want to stress to you. If you will insist on mixing together things that could produce an explosion, do please add a little water to each first. Mix them into a moist paste with water, and then you can dry out small quantities as required. It's much safer that way. Never perfectly safe. Some years ago, a factory in Spain where they were making the cartridges for toy pistols was destroyed by an explosion. The building was razed to the ground and some 30 people were killed. So even in the hands of experts and using red phosphorus, it is not safe. I, however, have a method of producing a mixture of phosphorus of potassium chloride with yellow phosphorus, because on a brick over there, on a metal plate, I have some potassium chlorate, and I have here a solution of yellow phosphorus in carbon disulfide, and I'm going to pour some of this onto the potassium chlorate. Now, I always like to perform my experiments in duplicate or triplicate, and so we have some more over here. Now, carbon disulfide is a very volatile solvent. And so, as it evaporates, it will leave every particle of the potassium chlorate coated with phosphorus. So we shall have an intimate mixture. That will then be an extremely dangerous mixture, which must on no account be approached very closely. It may go off spontaneously, but if it does not, I can of course set it off by the expedient that I used for the phosphorus in the flask. That is to say, by touching it with a warm iron rod. And the length of that is an indication of the respect with which I hold that mixture. Now this takes some time to mature. So whilst we are waiting for it to mature, let us think of something else. The oldest explosive, gunpowder, is, as you probably know, a mixture of sulfur, which burns to sulfur dioxide, of charcoal, which burns to carbon dioxide, and of saltpeter, or potassium nitrate, to provide the oxygen for the burning. When I was a boy, I tried to make some gunpowder, and I was rather disappointed in it. It seemed to burn rather slowly compared with the commercial powder. Because, you see, in my young days, one could buy commercial powder at the drugstore or the grocer's. Because in my coal mining area, the miners had to provide their own powder for shot firing. And so the boy of the family would be sent to buy a couple of dozen bobbins of powder. And so when I had tuppence, or the equivalent of 4 cents to spare, I bought a bobbin myself. Couldn't afford many of them. And so I tried to make some myself, and it was much slower than the commercial powder. But I found that when I put some of it into a bit of copper tubing and pinched up the ends so that it was confined and suspended it over a candle flame and retired to a suitable distance, I got a very good bang out of it. But it seemed so inferior that when later on I read in Prescott's Conquest of Mexico that the Spaniards, having exhausted their supply of gunpowder, made their own, and it worked, I was rather skeptical. You see, there were niter beds from which they could get saltpeter. Charcoal was easy enough, but for the sulfur, they needed a volcano. Well, they happened to have one handy. Indeed, it's still there, south of the border, down Mexico way, Popocatépetl. I think the locals call it Calippo for short. But for sulfur, they had to get to the crater, and it's over 17,000 feet high. So they first of all had to hack their way through the jungle, then over lava-strewn slopes, then through snow and ice, and when they reached the crater, they could see the sulfur, but it was several hundred feet down. So they drew lots. And one Francisco Montana, who drew the wrong bit, was lowered down by ropes by his companions, and he had to hack the sulfur off the walls and send it up in a basket. And eventually the people up at the top were satisfied with the amount that he got, and they remembered to pull him up, and down they came, ground all these things up together, and according to Prescott it worked. Well, as I say, it didn't seem to me that mine would work unless it was very closely confined. And so I think possibly that story is correct after all, because in the barrel of a firearm it is confined. Now, on television or on films, you see someone throw a match at a barrel of powder and up it goes. Let us try it. I have here a sample of commercial powder, and I'm going to pour some of it out onto the base of this tin. And notice that I'm very careful, having done so, to close the can, put it away, covered up, and remove it well away from what I'm going to let off here. This is a very important precaution. Whenever one is using an explosive or fireworks, the main stock should always be covered up well away so that no spark can get to it. So now we will try to set it off. And it extinguished the flame. This does not mean that I recommend gunpowder as a fire extinguisher. You can't rely on that happening. But what you really need to set it off is a spark. And so you need a fuse. A fuse, because the function of a fuse is to produce sparks. However, we have been somewhat rudely interrupted by one of those things over there, and so I will let this off and then break the continuity a bit whilst I deal with the others. And so although the flame failed to fire it, the spark set it off. But notice that when it did, there was no bang, just a puff. And notice also that the base of the tin is still flat. This is because gunpowder belongs to the class of explosives that we call deflagrating. There's another class that we call detonating. Sometimes we call the deflagrating ones low explosives and the detonating ones high explosives. And the difference between them is the difference in the rate at which they generate energy. With the deflagrating explosives like gunpowder, you're generating the energy at speeds below the speed of sound. And so, you see, the gases are generated at such a speed below supersonic speed that the atmosphere has time to get out of the way. The detonating explosives, so the deflagrating ones, generate their energy at hundreds of meters per second. The detonating or high explosives generate it at thousands of meters per second. And so, developing it at supersonic speed, the atmosphere acts as a barrier, and they can affect the surface on which they rest. So they can shatter a lump of rock or a steel girder because the pressure is concentrated on the surface by the sound barrier of the atmosphere. But now, as I say, one of those things has gone off, so perhaps before I proceed further, and to avoid being further rudely interrupted, I'll borrow your coat, I think, Frank. No, I'll have yours. And we'll tuck this out of my shoulder. And we'll have the mask. And two. Oh, yes. Light me another flame, will you? Now, whilst I'm warming up this rod, let me draw your attention to what we have. On the brick, on the metal plate, there is some potassium chlorate which is now impregnated with phosphorus. And so one of the effects is the burning of the phosphorus in the oxygen of potassium chlorate. But there is another effect. Most compounds are formed with liberation of energy. You see, the burning of the spirit in those lamps is generating carbon dioxide and water. And these are stable substances because obviously, since energy has been liberated in their formation, they have less potential energy than the material from which they are derived. So the carbon dioxide and water are formed in an exothermic reaction. But some compounds are formed with absorption of energy in an endothermic reaction. They have, so to speak, extra energy built into them, and it's fairly bursting to get out again. And potassium chlorate is an endothermic compound. So we shall get some energy from the potassium chlorate itself, liberated instantaneously. Now, the reason I took these precautions was because when I was doing this for British Broadcasting Corporation, on the rehearsal, the steel bar bent a good deal. And the producer said, "Oh, that's good, keep that in." And so I provided him with some, I thought I'd give him good value, and so I put some extra on for the actual show, and the iron bar doubled itself and hit me on the head. And this was going by landline to the studio, and they stopped recording and said, "We're sending an ambulance to take him to hospital." So I said, "Rubbish, just get the makeup girl to clear it up so that the blood doesn't show." And we'll carry on, which we did. But thereafter, I have taken the precaution of protecting myself. And I was a bit dubious about the steel bar tonight, and so I strengthened it with another one, and so it didn't bend quite as much as I had hoped. But it will, I think, illustrate what we want. I said the potassium chloride was on a metal plate. The plate, in turn, was resting upon a coin. A coin, I'm using a British coin which is out of date. So I think I'm within the law in that. And you see it has cut out the shape of the coin in the aluminium plate. And I have here the bit that's cut out, bearing the effigy of Her Majesty Queen Elizabeth II. And so this illustrates not only that you can get an explosion with potassium chloride and phosphorus, but also an important application of explosives, impact moulding or explosive forming. Of course, they don't use potassium chloride and phosphorus. They use a commercial explosive and in a confined space. And the best way of confining it is to do it under the surface of water. Just pass that round so that people can have a look at it, will you? Hold it by the edges in case there's any phosphorus there. And can you pass, there's the bit that's cut out. Can you pass it up, half of it one way and half the other, up to the back? Well, as I say, it is an example of an application of explosive impact moulding, which is a very useful process. because, you see, it's very cheap. If you wanted to mold something, you'd have to set up mechanically, you'd have to set up a very expensive press to do it. But here, a few pence worth of explosives will do the job. Of course, they don't use potassium chloride and phosphorus. They use a commercial explosive in a confined space. And the easy way of confining it is to do it under the surface of water. One application of this, which has not been exploited commercially as far as I'm aware, was the moulding of stainless steel plates for dentures. You see, a plaster of Paris mould is taken of the gums, put under the surface of water, a bit of stainless steel over the top, the explosive over that, and when it is let off, you get a perfect impression in the steel. Although the plaster of Paris is brittle, it stays in shape long enough to take the explosion. But it does make rather a noise, and so I'm afraid it's not been exploited as it should be in any large town or city. However, an allied application is the explosive welding. Some metals cannot be joined by any conventional welding technique. For example, steel and titanium. But if you have a base plate of the one and a sheet of the other, and put the second one over the top, cover it with sheet explosive and then detonate it, as it slaps down, the two are firmly welded together. It doesn't seem to matter if there's a certain amount of impurity on the surface. It is swept out by the force of the explosion. And if you cut a cross-section of it, the two seem to be practically dovetailed the one into the other. They call it cladding one method with another. And the largest piece that I've heard of being done in that way was, I think, about 4 feet wide and 20 feet long. Done, of course, in the United States of America. And so here is something that you can do with explosives that you could not do in any other way. Now, when we were... we'd only let off some gunpowder. I was going to show you the effect of confining it. As I say, I thought that possibly where it was confined in the barrel of a weapon, it might work better. And eventually I acquired a weapon with which to try it. This is a very old pistol. It bears the name Nock, N-O-C-K. He's referred to in the Beggar's Opera. Presumably he supplied Macheath's highwaymen with their pistols. I think it may originally have been a flintlock pistol, modified to take percussion caps, when the percussion system of ignition was invented early in the last century by Dr. Alexander Forsyth, a Scottish minister. He was a Scottish clergyman. He was the minister of Belhelvie, just north of Aberdeen. And when I was lecturing at Aberdeen, I went to Belhelvie to see if there was any memorial to him there. I couldn't even find a church. And there are only about a dozen houses in the place, so this perhaps accounts for the Reverend for his reverence to be able to carry out some experiments with explosives. What he was trying to do was to devise a dark form of ignition for his fowling piece. You see, with a flintlock fowling piece, the flash of the flint frightened the birds so that they were away before the shot arrived. So he developed this dark form of ignition. It was successful, and so the government provided him with facilities in the Tower of London, experimental facilities, so that he could carry out his work. And the percussion system, although modified, is still used today. In fact, the successful modification of it, so as to render it much more usable for military purposes, the successful application, of course, took place in the United States of America. And so we have the pistol, and so I will load it up with commercial powder and see how it works. I have a powder flask which has an adjustable nozzle for delivering various measured quantities, and I've opened it out to the fullest extent. And so I'm pouring a charge of powder into the pistol. Well, I suppose you're only supposed to use one charge with a pistol, but this is a large room, so we might try two. In fact, it's a very large room, so I think we can stand three. And notice that I'm very careful to put the powder flask away, covered up, because although it is enclosed in the powder flask, there will be a certain amount of fire and flame going on later on. And if some burning cotton wool, for example, should fall onto the powder flask lying on the bench, it might put a premature end to the lecture. And so you cannot take too many precautions with these things. Now, having put in the powder, we need a wad to hold the powder in position. For this purpose, I'm using cotton wool. People sometimes call this wadding, because, of course, it's used for making wads. And so we ram that down on the surface of the powder. Now I'm going to put in the bullet. But in deference to you, I'm going to use another bit of cotton wool to represent the bullet. And so we ram that down as well. Now, in the days when these things were used in anger, of course the bullets were round leaden balls, which had to be a little bit smaller than the barrel in order to go round at all. So if at this stage you tilt the muzzle downwards, of course you'll lose your bullet. And so we need another wad to hold the bullet in position. You will realize, therefore, that the products of combustion, the gases from the burning of the powder, are now no longer free to expand to the atmosphere. The stuff is closely confined, and it will be interesting to see what effect, if any, this has. So what we have to do now is to apply a percussion cap to the nipple and hope for the best. I say that because I used to have some percussion caps that were over 100 years old, and they always worked. Whereas those that I buy nowadays sometimes fail. However, if we don't succeed at first, we have to try again. And so here, if it goes, is the effect with the powder confined in the barrel of the pistol. It did not go. But notice, I don't lower the pistol. I hold it there. It might be a hang fire. Hang fires can last a minute or more. And so you see, if when I pressed the trigger it didn't go, I were to drop it, I might shoot one of you by the hang fire, and I'd rather not. And so I wait. And this is a point to remember. With either fireworks or explosives, if the thing does not go off when you expect it to, wait. It could be a hang fire, and you have to wait a sufficient time to make certain that that's not going off, and then devise some means of dealing with it. Well, so this is a precaution one should always take. Well, let us try another percussion cap. This, by the way, sometimes proves to be an incendiary bullet. So if any of it comes your way and sets anyone on fire, let us know. We have some fire extinguishers, and so Dr. Palmer will extinguish you. Try again. And you see. I think you will agree that the powder went off more rapidly where it is confined. Now, there must be some reason why confining the powder makes it go more rapidly. It's a general principle, and it also brings out the lesson that one must never confine any firework or anything of that sort which is not intended to be confined, because something that could be quite innocuous when let off in the open air may become very dangerous if it is confined. Well, as I say, there must be some reason why confining it makes it go better. And so we might see much better what is happening if we carry out an experiment in a glass tube. And so I'm going to ask Dr. Palmer to do this for me whilst the old man has a rest. He has a tube there, which, before we started, he filled with nitric oxide, a colourless gas. And he's going to add to it a little carbon disulfide. There's already a lot of liquid in the tube. That is water, and I'll explain the reason that is there later. And so he's mixing these up thoroughly. And you see, nitric oxide contains oxygen and will support combustion. Carbon disulfide, of course, will burn. So here we have the possibility of combustion. But notice nothing has happened. In fact, we've sometimes kept such a tube for a week without any perceptible change. But one important principle is that the rate of a chemical change is doubled or trebled or even quadrupled for an increase in temperature of 10 degrees centigrade. And so if he excites the molecules by bringing up a lighted taper to them so that they move more rapidly, they can then surmount the barrier and an effect will take place. Now, I don't know whether you saw exactly what happened there. What I saw was that although the flame started slowly, it seemed to be building up speed as it went on. Now, I always think it's a good idea to do things in duplicate. Have we another tube, Frank? We have indeed. And so this is a rather larger one, and we may be able to see the effect rather better. I think what is happening, you see, is that the warmth of the taper, as I say, excites the molecules so that their rapidity of motion is increased and they can react. Then the burning of the first portion warms up the mixture next to it, so this starts at a higher temperature and therefore goes more rapidly. And this warms the next bit still more, and so we get this accelerating effect all the way down the tube. There is another effect here, because the burning of the first portion will, of course, generate pressure, which will tend to compress the remainder. And if you compress a gas, you generate heat. I don't know if anyone ever pumps up a bicycle tire with a hand pump now, but in the days when they did, they would notice that the pump gets warm. If you compress a gas, you generate heat. And adiabatic compression, so rapid that the heat generated has no chance of escaping, can raise the temperature hundreds of degrees centigrade. Well, you would be able to see the effect there. But as I say, we usually do things in triplicate. Do we happen to have another one, Frank? And so I think this accounts for the way in which it increases in speed as it goes down. Now, there are some very complicated chemical reactions will be taking place in this tube. I have no doubt that free radicals are involved in this process. But there are these two simple effects, that of the temperature and pressure. Now, I said I would explain why there's some water in the tube. An old way of filling the tubes with nitric oxide was to have them open at both ends and pass nitric oxide in at one end until no more brown fumes came out at the other. Because, you see, the nitric oxide combines with oxygen of the atmosphere to produce the brown nitrogen tetroxide. Now, on one occasion when this was being demonstrated before the French Academy, because it's a very old experiment, the tube detonated. and some of the audience were cut very badly. In fact, I think one of them died as a result of it. And so we have a tube closed at one end and collect by displacement of water in which the tetroxide is soluble. Because you see, in the experiment at the French Academy, working in those days by lamplight, of course there might have been some of the tetroxide left in the tube, but in a yellowish light they didn't notice this. And so I think in those circumstances you could get an explosion. So we always collect over water, so there's no tetroxide there, leave some water in it, which not only helps to mix but also serves to take up any tetroxide which is formed when we're putting in the carbon disulfide. Nevertheless, we always use one screen to protect the audience and another one to protect the operator. Now, this device was also, at one time, used as a means of taking flashlight photographs, because the light emitted is highly effective on the old-type photographic emulsion. May possibly account for somewhat startled expressions in some of those old photographs. But I think it helps us to explain why the powder goes off more rapidly where it is confined. Because the heat and pressure from the percussion cap and from the burning of the first few grains of powder will warm up all the air surrounding all the other grains, so they start at a higher temperature and therefore go more rapidly. If this is so, we should expect that lowering the pressure would slow things down. It does. If you have a vessel that can be evacuated with a wire running through it that can be heated electrically, you can cover the wire with gunpowder, then raise it to a red heat by an electric current without any of the powder going off except the particles immediately in contact with the wire. It doesn't spread to the rest of the mass, provided that you have pumped out the air and lowered the pressure to about 10 millimeters of mercury. So lowering the pressure slows it down, raising it sends it up. And so you see, you could not set gunpowder off on the surface of the moon, for example, in a vacuum. Lowering the pressure slows it, raising it makes it go far, far faster. And so once again, something which is intended to be let off in the open air must never be enclosed. Now, from what I have told you about the difference between deflagrating and detonating explosives, you might think that the detonating ones would always be superior. Can we have more illumination so that I can see? I want to be able to see what the theatre is like up there. Yes. Indeed, for a propellant, you see, you need something that doesn't go off so rapidly, something that will explode relatively slowly and give a nice heaving action instead of a short, sharp shock. And so the good old-fashioned gunpowder is almost ideal in this respect. It has certain disadvantages, but it does have this slow heaving action. And to illustrate this, I'm reversing the ordinary arrangement. You see, normally the firearm is an object which has a very large mass compared with that of the projectile. And so, although the firearm recoils, the extent of the recoil is much less than the distance traveled by the projectile. But here I'm reversing this. My firearm, what are these walls made of, by the way? The firearm is a thin aluminium case, the sort of thing that redoxin tablets come in. And the projectile is a wooden spigot which is in this retort stand on the stool on the earth. So the mass of the bullet is infinite compared with that of the firearm. And so here we shall not see the projectile move. What we shall see is the recoil. And I want to see if we can impart considerable energy to that recoil without splitting the thin aluminium case. Has that one stayed up there? Well, if you recovered one, I think if you examine it, you'll find that it is not split. The only hole in it is where I put the fuse in. And so, as I say, this illustrates the value of a low explosive, like gunpowder, as a projectile, as a... Thank you very much. Yes, it has dented it. Well, wait a minute, you could take it back again for people to have a look. It has dented it, but it's not split the case, although it's only very thin aluminium. Thank you very much. I'd like to give you another example of this. You may possibly have read or heard that one can shoot a tallow candle through a barn door. We have no barn door. But in lieu of that, I have some pieces of plywood. A very tough material, and they're spaced so that we can measure the penetration, if any. I want it putting on that side because there's a clock here. And behind the plywood, I have a brick. And behind the brick, we have a steel plate. So the fabric of your building is fairly safe. Now we need a suitable weapon. And it so happens that I have one here. This is a very old musket. Bears the date 1857, and it still works. And so I'm going to load this up in pretty much the same way as I did the... yes, we'll have it on this side. As I did the pistol, except, of course, it's a much longer barrel. And so I'm first of all going to put in a charge of fine powder so that it will get into the nipple of the musket. And I'll then use a coarse powder because, you see, always the size of the grains was adjusted according to the length of the barrel. You see, for artillery purposes, guns, when they first used ordinary powder, they found that it wasn't as good as they expected because the effect is produced so quickly. What you want is for the burning of the powder to proceed whilst the projectile is being pushed up towards the muzzle. so that it gets its maximum pressure again. For a pistol, of course, with a short barrel, you want a very fine powder. But for a musket, you want a coarser one. And for the artillery, for the big guns, they use, first of all, lumps of powder. But then you see, as the lumps burn, their surface area is decreasing. And so the rate of production of gases is falling off all the time, just when you really want it to be increasing. So they then made the powder into hexagon shapes with a hole down the middle. So the burning of the interior surface, which would be enlarging all the time, would compensate for the diminution of the exterior surface, and they got much better results that way. They called it prison powder. Now I've got to judge the amount to get through this plywood, and so this is an art rather than a science, and but I think that might do. And so we'll pour this down the barrel. It might, I think, be well if I had a bit of padding in my shoulder, because this thing can kick like a mule. So put that handy for me, will you? Now, having put in the powder, we need, on this occasion, we need a wad. Now, in fact, they didn't need a wad in later days, because they then had an elongated bullet in a paper case, and so all they had to do was bite off the bullet, pour the powder down, and ram the bullet after it. And an elongated bullet, of course, would there was no chance of it coming out again. But I'm using a wad because I'm using a tallow bullet. And if I didn't use a wad to protect the tallow, of course all that might happen might be that we would get a squirt of molten tallow coming out of the open end, and this would rather diminish the effect that I want to show. And so there is the powder in and a wad in. Now we need a bullet. The tallow candles were made by dipping a loop of wick into a bath of molten tallow and repeating the process until they're built up to the proper extent. I have one here that have been cut off from the loop, and I'm pushing that down the barrel. Now, as you see, you couldn't maintain a very rapid rate of fire with these things. Indeed, from the point of view both of rapidity of fire and of accuracy, the musket of Waterloo was greatly inferior to the longbow. Of course, there they were using a round ball, and it was before the elongated one had been developed. And you see, the round ball being pushed along the barrel will rub against the side and develop a spin, an unpredictable spin, so that it will swerve as it emerges from the muzzle, just as when you slice a drive at golf or cut a cricket or tennis ball. It will swerve in a quite unpredictable manner, and you can miss the target by 10 or 12 feet at 100 yards. And so, as I say, it was inferior to the longbow, because a good archer with the longbow could get several arrows in the air at once, and Henry VIII passed several laws concerning it. One of these was for the practice of archery. It was compulsory for all males over the age of 22 years to practice archery every Sunday at ranges not shorter than 200 yards. 200 yards was considered to be a boy's range with the longbow. Yet at the Battle of Waterloo, the effective range of the musket, Brown Bess, was only 60 yards. If you're 100 yards away from a man, he could hit you only by accident. And so the only reason the musket succeeded in war was because the noise and the flash and the smoke frightened the horses of the enemy's cavalry. And so what we have to do now is to apply, I think perhaps I'd better have a little padding. because it does kick. What we have to do now is to apply a percussion cap to the nipple. And we'll see what happens. And well, it has gone through the first one, and it has gone through the second one. Pass them up so I can see them. It has gone through the third one. It's going a bit sideways now, you see. And it has gone through the fourth. The hole gets bigger and bigger as it goes on. And I demonstrated to you that I had a brick behind it. I now have two half bricks. So that even after passing through an inch of this quite tough material, it still has the strength to break a brick in two. So you see now why we have a steel plate behind that as well. And so this old story is quite correct. In fact, I have tried it on, you see here, the plywood is a flexible material, and it was not firmly held, and so it can tend, so to speak, to ride the punch, whereas a more resisting barn door would be penetrated more easily. I've tried it on firmly held planks, and it'll go through 4 or 5 inches of solid timber. So that old story is quite correct. Now, I think we're due for a slide, are we not? Oh yes, I want to draw your attention. I've made a scale there. It's not absolutely accurate, but it gives you an indication. It's a logarithmic scale, and so a bit of line sticking out above the one above, of course, means thousands of times greater. And so here we have the Krakatoa Island explosion, thousands of times greater in power than that of the hydrogen bomb. The hydrogen bomb, in turn, much greater than the atom bomb. Here, this represents the biggest accidental explosion, and this one, the biggest commercial explosion. The record for both, of course, being held by the United States of America. That was the biggest bomb dropped by aircraft in the Second World War. This, the hand grenade, the detonator, and these percussion caps that I've been using. We've indicated there that that the more intimate the mixture, the more rapidly we would expect the thing to go. So that a mixture of gases will go more rapidly than a mixture of solids. Now, one should never make a prediction of that sort without an experiment to prove it. And so we have prepared some mixtures of gases, which we forgot to put out, by the way, and so Dr. Palmer has gone to fetch them. And here we are. Now these, so you don't have milk bottles in the United States, and they're the most suitable bottles for the purpose, so I've had to bring these all the way from England. This contains a mixture of methane, natural gas, and oxygen. The black is the volume of the methane, the white the volume of oxygen to burn it. And you see it requires twice the volume. Methane requires twice its volume of oxygen to burn it to carbon dioxide and water. This is just the opposite of the old gas which we used to have, which was made from coal, because there it was largely hydrogen and carbon monoxide, and these require only half their volume of oxygen to burn them. So they're much more, this is much more concentrated. Then we have a different hydrocarbon here, ethane. Isn't it ethylene? That's the ethylene. That's butane. No. Thanks. That contains methane. Methane is CH4. Ethane is C2H6. 2 atoms of carbon and 6 of hydrogen instead of 1 and 4. And since equal volumes of all gases under the same conditions of temperature and pressure contain the same number of molecules, obviously, if the one molecule contains twice as much carbon as another, it needs twice as much oxygen. And so, you see, the ethane is more concentrated. There's more room for the oxygen, and so we would expect that to be a better explosive. Here we have butane, C4H10, 4 of carbon, 10 of hydrogen. Much more concentrated, much more room for the oxygen, and so we would expect that to be better still. But here we have ethylene or ethene, which is poorer in hydrogen than the ethane, so it takes up more space, and you might think that that is going to be inferior, but it is endothermic, and we shall find out what that means. I have another hydrocarbon here, ethyne or acetylene, and this is poorer still in hydrogen, so it takes more space, and you might think that that is certainly going to be inferior, but it is powerfully endothermic. I'm going to put that away for a moment until we see how it behaves. And so it's interesting to be able to see an explosion take place, and so we will re-erect the screens so that I can carry out the explosion in the screens. Take those 3 bottles at the back, please. We have to check carefully that we have got the right bottle. And of course I need some protection. So here we have methane and oxygen. I'll turn the unpainted side towards you so you can see the explosion take place. And you see we have an explosion, but nothing particularly dramatic. We would expect the ethane to be better. Well, theory and practice seem to be working pretty well together, but when we come to butane, therefore, we expect it to be more powerful, so I think it might be well if we use a metal cylinder instead of the plastic screens. Well, I think certainly that was more powerful. Now when we come to ethylene, we're not quite certain about it because it's endothermic, and we don't really know what difference this might make. And so, to get an indication, I'm going first of all to let off a bit of gunpowder in some filter paper, the flask. Gunpowder enclosed in filter paper, which doesn't enclose it very much. Put this away carefully, please. And so I will, to see what the confining effect of filter paper is. Well, it's not a lot, you see. Now for comparison, I have a packet of silver acetylide, and I have drawn the diagram somewhere, I think. No, well, you see, in ethane, the carbon atoms are quite a way apart, 1.52 angstrom units. In ethylene, they're closer, and in ethyne or acetylene, they're only 1.2. In other words, the atoms have been squeezed together. That's where the energy has gone that you have put into the thing in its formation. And in silver acetylide, we have the acetylene or ethyne with the hydrogens removed and replaced by silver atoms, which gives us a solid which we can investigate. And so I'm laying that on the surface of the tin, which you will recollect was not dented when I let off gunpowder on it. And so I'm going to put some more gunpowder on the top of this silver acetylide so as to ensure that the heat will get through the paper. I'm waiting until it's out of the way. And whereas the gunpowder failed to dent the tin, it remained perfectly flat, this one has dented it. And so that illustrates the fact that the energy there was developed much more rapidly than it was with the gunpowder. And so, since we know, therefore, that an endothermic compound such as ethylene can develop more energy, we take another precaution here. Well, I think it was not inferior. I am not going to let off the acetylene with a taper. I shall use a fuse for this purpose so that I can get out of the way. Now, I used a bottle that I'd painted to indicate the volume relationships, but the one that I'm going to let off I didn't bother to paint, just to put a line round to indicate the volume of the ethylene, for a reason that may become apparent to you a little later. For this purpose, I'm going to set it off with a fuse so that I can get out of the way. Now, you might think that this is cheating, i.e. that I am enclosing it. Well, I try not to do so. I try in the first place to put it in as loosely as I dare. I don't make it too loose in case it should drop into the bottle before I can get out of the way. And also I try to arrange it so that the end of the fuse is in the cotton wool. So what I hope will happen is that the fuse sets fire to the cotton wool, and this in turn fires the mixture. So what I hope is that at the moment that it goes off, the neck of the bottle will, to all intents and purposes, be open. This is about a 15-second fuse, or perhaps a bit more. And acetylene is very powerfully endothermic. Hence its use, of course, in welding, and because of the intense heat generated in addition to the ordinary heat of combustion. And whereas the other bottles remained intact, this, you see, has been reduced to a very fine state of division. This illustrates the powerful shock effect that you get with these endothermic compounds. Endothermic compounds such as the old one was mercury fulminate, lead stiffenate, lead azide, and so on. These are used in percussion caps and detonators to initiate the explosion of larger quantities of less sensitive explosions. I'll now ask Officer Powell to help me. You see, the silver acetylide was only enclosed in filter paper. In a detonator, the active material is not only enclosed in a metal tube, but it is also compressed. And we want to see what difference this makes. So we're using the same tin, which was unaffected by gunpowder, dented somewhat by silver acetylide, and now we're going to see what happens when we have a detonator on it. Notice that the detonator is crimped onto the end of the fuse, so that it is held there, because of course there is a certain amount of jet propulsion when the fuse is burning, and so it's important that the detonator is secured. I think this slide might be more convenient. Is it all right?
You'll have to wait approximately 40 seconds. So you can all guess. Oh!
Now, there is another principle involved here. I say that the active material is in a metal tube. It is compressed in that with a pressure of about 2,000 pounds per square inch. Well, you might think this ought to send it off. It does sometimes, so they do it by remote control. But although steady pressure won't do it, pricking it with a needle would. There's another point. The end of the metal tube is dimpled, so that it has a shaping effect and will focus. Where's the tin? Oh. And so now, so again, the enhancing effect of confining and compressing the material. Well, now we've had, you see, mixtures of solids and mixtures of gases. We might mix it by having, say, a mixture of a solid and a gas. I have here a finely divided solid like a podium, so finely divided that I can draw it up by suction into a glass tube. The lights down, please. If now I project it through the flame, as you see, we get very rapid combustion, no explosion, because the gases are free to expand to the atmosphere. And so any inflammable, finely divided material mixed with air can cause a nasty explosion, and this used to occur in coal mines until they devised ways of combating it. Now, in these cases, in gases, we're dealing with large volumes. If you want to get it more concentrated, one way of doing it would be to use liquid oxygen. Now, liquid oxygen starts at a grave disadvantage as a means of generating heat. And to illustrate the low temperature, I'm going to use in the first place liquid nitrogen. Oh, well, I want nitrogen first. And you can tell, I thought when I poured that out that it was oxygen because it's blue, whereas the nitrogen is colorless. And you see it boils vigorously because of the heat in the glass. There are various ways of demonstrating the low temperature. One simple one is to take a nice flexible piece of rubber tubing and kink it and plunge it into the liquid gas. It boils vigorously by reason of the heat in the rubber. Notice the importance of kinking it when you do this experiment, because if you don't, the liquid gas gets into the tube and boiling there acts as a pump, and it comes squirting out of the open end, and you spray either yourself or the audience, and this is not very good because it's so cold. And you see that the properties are now completely altered because it is extremely brittle. Having used the nitrogen for that purpose, we can get rid of it. I can't do this with oxygen because we might all go up in flames, but it's all right with the nitrogen. We now replace it with oxygen, and to see whether it can overcome the disadvantage of the low temperature, I'm going to soak something in it and burn it. Take this away. Where are the spills? The bundle of spills, you know that these will burn, but not all that rapidly. We need a light as well. So I'll soak them well in the liquid oxygen. Lights down, please. And as you see, they do burn pretty rapidly when they are soaked in the liquid oxygen. But that was a very coarse sort of material. It would be interesting to try something more concentrated. Something more, well, absorbent. And so I have here a suitable material, cotton wool. And I'm going to soak this in liquid oxygen and then fire it. And I now want some volunteers with fire extinguishers. Now I'm going to soak that stuff with liquid oxygen and then put a light to it. And when I do, I want you to step in and blast everything with carbon dioxide. Don't be too premature. Let me set it off first. Move that fire extinguisher.
Right, come back this side. Okay, get ready. As soon as he hits it, you hit it. Right, yeah, everything.
All right, the lights down, please. Have you got...
Okay. Okay. Get ready, start going.
It's still on fire. There should be a slide on now. That's right. Well, on one occasion when I was doing it, someone took a photograph, and so I had this slide made from it. You may observe I'm not wearing any protection there. It was after seeing that picture that I started wearing protection. Now, I've tried to indicate some of the general principles of explosives and some of their uses. Their uses, of course, are so numerous that you'd require a whole encyclopedia to deal with them. But apart from the apart from the large-scale use in mining and construction, there are all sorts of small ways in which they save muscle power and manpower. For example, in modern buildings, ceilings are suspended from pegs fired into the concrete or the steel girders by means of what I call an explosive hammer. The makers call it a cartridge-assisted fixing tool. It's only a small cartridge about that size, but it will make firm fixings in steel or concrete much better than having to drill a hole and put a screw in it. The shaping of a charge has an astonishing effect. If you have a metal cone coated with explosive, when it's detonated, it produces a jet of metal which will go through several inches of steel or several feet of concrete. Used in war, in piercing the armor of tanks and the concrete of dugouts, used in peace in petroleum technology, when you have to drill for oil down to 10,000 feet or so through water-bearing strata. So you have to line it with a steel tube, and you then have the problem of drilling a hole sideways about 10,000 feet down to let in the oil. Well, they used to do it by blasting the whole tube to bits, but it's better to use a shaped charge. In the United States of America, the jet axe was developed some years ago, which will enable you to blast a hole through a reinforced concrete wall, so that if a building is on fire inside and the entrance is blocked and the people can't get out, by slapping this against the side you can instantaneously blast a hole through, which would either enable them to escape or let a fireman in with his hose. And of course, you could not have made our railways in the past or our motorways. You could not have explored for oil, and you could not have done construction generally without the use of explosives. So although we commonly associate explosives with war, their value to us in peace vastly exceeds the damage that they do in war. So one of the Gilbert and Sullivan operas was being performed. One of the ladies in the audience came up to Sullivan thinking he was Gilbert. Came up to Gilbert thinking he was Sullivan and said, "I do so admire your music. You so remind me of dear Mr. Bach. Is Mr. Bach still composing?" "No, madam, decomposing." I never fail to get in that quote from W.S. Gilbert if I can. But he also provides me with my excuse in the Yeoman of the Guard, when, "For he who'd make his fellow creatures wise should always gild the philosophic pill." And of course the modern variant on this is that a spoonful of sugar lets the medicine go down. So although there may be a certain amount of entertainment in what I've been doing, it has a serious object to indicate the precautions one must take in handling hazardous materials. And so I hope that you will notice these precautions, and if you do experiments, you will never have any accidents. Thank you. Well, after such a round of applause, of course, I think I must give you an encore. And to illustrate another point, that even finely divided metals are inflammable, and in a confined space could produce an explosion. Some years ago, our professor of music at Nottingham wanted to do a Berlioz festival, including the funeral march for Hamlet. And he came to me, he said, "You know, the closing lines of Hamlet are that they have a peal of ordnance." He said, "Now on the stage they do it with a drum beat and it's not effective. Can you do me a peal of ordnance?" Well, of course I could, because apart from my other weapons, I had 2 First World War German very light pistols, and I had adapters made to take blank cartridges. And to illustrate the point tonight, I've put a teaspoonful of magnesium powder down each of them. And so, you know, the closing lines of Hamlet are, "Take up the bodies, such a sight as this becomes the field, and here seems much amiss. Go, bid the soldiers shoot."
Come on,